After you open Quartus, you create a new project. I make a new folder which will be the working directory for my project. So this is the name of my project, and I'll change the top level design entity name for this project, as Qsys is gonna have the same top level entity as Quartus. In the device and settings, we have our DE1 board with the pin count of 484 and the speed grade of 7. In EDA tool settings, we have model sim for simulation, and our hardware language is Verilog HDL. After creating the project, we need to integrate our system. For that, we use the Qsys tool. Qsys basically captures system level hardware designs and automates the task of defining and integrating customized components. It automatically creates an interconnect logic from the high level connectivity you specify with. Here we create a new component for our design. For me, the component name is FIR, filter underscore FIR, and the display name remains the same. In the group tab, we make our own group which will collate other connections. Let's include all the Verilog files which will describe our hardware. We explicitly need to specify our top level file here. All these files make up my FIR filter design. Hit the analyze button for it to analyze the system. We can customize our parameters for reuse of the design. The signals you see here are signals from a top level module. The components which I have designed will have these interfaces, which will just make sure that all the reset pins are synchronized with respect to clock here. Press finish and save the custom component design which is generated here. Now in the search bar, type in NIOS 2 to add components or modules. We use the economical version of NIOS 2 since it's free and no license is required. It supports up to 256 custom instructions and up to 2 GBs of external space. It has the JTAG debug module. It completes the system in fewer than 100 LEs. After this, we add the memory module, the on-chip memory module. After having added the on-chip memory module, we add the JTAG UART to communicate with the system, which is our computer. After this, we need the performance counter to calculate the component's performance. Having added the performance counter, we add the custom FIR. We can change the component's parameter, that is to reuse it elsewhere in some other project. We now add the clock to all the system components as well as reset. The processor here has 2 ports, that is the data master and the instruction master. These instructions need to go to all other connections. All the blocks receive the data master for its communication. We also make sure the interrupt pins are connected. After this, we now assign the base address to all the components by we still might have some errors. To get rid of those, we assign the interrupt and reset vector to on-chip memory to allow us to generate the system. Here, Verilog files are generated for the system. After you hit generate, save the system. Name should be exactly same as the top level entity in Quartus, as the top module remains the same for both Qsys and in Quartus. After generation, we add the QIP file in the project. Qsys creates a folder wherein we have the Verilog files which automatically generated. You can either import all of them or just import the QIP file. After this, we now need to assign pins for the clock. Since all components are built in FPGA, we just need to assign the pins to the clock. Location of the clock is pin underscore L1 and it uses a standard 3.3 L VLV TT value. After having done this, just save and compile the assignment editor. While the system compiles, in the meantime we can go to NIOS 2. Just make sure that the work directory here remains the same. Initially I was getting errors here because my work directory was different, but having done it repeated number of times, I eventually got to know that the work directory has to be the same. The simultaneous compilation in Quartus will produce a SOP file which will represent the system. Now this file will be put in the D1 board. Here we can see the percentage of our design which is being compiled. Now we have the complete compilation of the system. We now go to the programmer wherein we have our hardware setup. Using the USB blaster, we import the SOF file here and burn it on the board. The NIOS 2 chip will now have the system burnt in it with all the components that we have added earlier. The NIOS 2 processor has to be programmed since it gets the input values and gives out our final output values. For this, we create a new project in NIOS 2 and we name the project accordingly. The SOPC file is generated automatically. And while it's getting added, we have to make sure that the project name and the project location are belong to the same directory, because if you don't do this, it'll end up using the default location for the project. To test our design, we use a template to test the system. NIOS 2 provides us with a hello world.c file. You build the project by running it and input values to the already implemented FIR, which is being burned in the FPGA. After the project is successfully built, you can see it's refreshing and making new files. We can replace the hello C code with the code which we have for providing the inputs and getting the outputs out of the system. So I have already copied the C file. Now all I have to do is just replace the hello world file with the C file I have. As you can see, the hello from NIOS 2, the system is working perfectly fine. We repeat the same process. We just paste our C code and now we'll run it on the NIOS 2 hardware. We have the performance counter in our system to check the system's performance. Values are sent in one by one through the memory interface to system, and as you can see we have the output here, which is -34, and the number of cycles in calculating the FIR is 15222. After this, we'll check the software implementation and then compare it with the hardware implementation. We need to check if or not hardware is faster than software.